I mentioned earlier when we were introducing chapter 12 that historically speaking, chemical equilibrium understanding, mathematically speaking, came before kinetics. But after kinetics was fully described, it seemed logical to study kinetics first because of the controlling influence that kinetics has on equilibrium. So that's why we did kinetics first. And now equilibrium, chemical equilibrium is and we go back to the idea of what's happening at the observable level, the macroscopic level, versus what's happening at the microscopic level. We observe in a chemical equilibrium situation where you have let's say reactants yielding products. That reaction can go both directions, and I think we've talked about that before. But as far as chemical equilibrium goes, what we observe is that at a certain point, the concentrations of the products remain constant, and the concentration of the reactants remain constant. But we know, or this is part of the theory, that reactions are happening at a furious rate. Even for the very slow reactions, the reactivity is very high, and they go both directions at exactly the same rates. So that's how we connect the microscopic and the macroscopic world. What it looks like in terms of concentration, and we're always the basic understanding is related to concentration of reactants and products. We'll talk about absolute amounts later when we try to reconcile equilibrium with stoichiometry. But this is what it would look like on the macroscopic level. We start off on this left-hand side with a certain concentration of hydrogen, nitrogen, and ammonia. Ammonia is at 0. So what that tells me is that we're starting from initial concentrations and no products available. So this would be like an initial rates situation. And the hydrogen decreases, the nitrogen decreases. The hydrogen decreases 3 times as fast as the nitrogen because of the stoichiometry. And then the ammonia increases at twice the rate that the nitrogen disappears because of the coefficients. Now, what we'll find is that in equilibrium situations, the stoichiometry, the coefficients of the balanced equation, are essential to calculating concentrations after a certain amount of time, once you reach equilibrium. So whereas in kinetics, we couldn't rely on coefficients to understand the reaction, in equilibrium, the coefficients are essential. And I'll get to that in just a second. Right, I already said this. The rate of the forward reaction is equal to the rate of the reverse reaction. That is the definition of an equilibrium, a chemical equilibrium situation. Actually, that could be expanded to any type of equilibrium, chemical or physical. All right. Another way to look at it is the rates of the reactions. The rates of the forward reaction is very high initially because there are no products to return rate. But the reverse rate starts to increase as we build products, and the forward rate decreases as we use up reactants. And at some point, they reach a position of equal rates, forward and reverse. And from a kinetic standpoint, the rate law would have that K value for the forward reaction at the beginning, right? And then the reverse would also have an expression for the rate law. But equilibrium says that the rates are equal, forward and reverse. Okay, so we're going to kind of tickle your senses here for a subsequent topic. Consider an equilibrium where you have water and carbon monoxide reacted together to form hydrogen gas and carbon dioxide gas. What do you think would happen if you add more water vapor? Notice the gas, water vapor to the flask. If we increase the concentration of water, what do you think is going to happen? Kinetics says that the rate should increase, right? At least temporarily. And some of the water will be used up. Some more of the carbon monoxide will be used up until we reach another rate balance. So the terminology, the parlance, if you will, of this description is the products are favored. When we increase the concentration of reactants, then the formation of products is favored until we reach equilibrium again. What if we add more hydrogen? Once we're at equilibrium now, we add more hydrogen. Now the reverse reaction favors reactants. And we use up some of the hydrogen that we added, plus some of the carbon dioxide that's already there. And we produce more water and more carbon monoxide until the rates balance again. All right, mathematical description of the equilibrium is credited to Peter Veg and his brother-in-law, Cato Goldberg. They were Norwegian chemists. It's surprising during the early 19th century, early to mid 19th century, how active the Scandinavian scientists were. The Danish, the Swedish, the Norwegians, they were very active in chemistry. Maybe that's because they didn't have much to do. Or it could have been long winters. It could indoor activities. It could have been the fact that they were industrializing at a rapid rate. Right. Anyway, what they devised was, in the process of solving a problem for describing chemical reactions, they differentiated between reaction rates and equilibrium situations. They had already gotten to that point by the mid 19th century. What they call reaction rates, we call kinetics. They call it chemical dynamics. And equilibrium, they call it chemical statics. Those terms are derived from physics. If you take a beginning physics course, the first thing you're going to study is statics. Opposing forces, things that just sit still, don't move. And we look for balance. And then you get to laws of motion. And then you work your way into energy. But they called it dynamics for kinetics and statics for equilibrium. And they were working with solutions, solution chemistry, and the terms that they settled upon that gave them the best results were in terms of concentration. So that would mean, for all intents and purposes, molarity. And this is what they devised. They said there's a constant associated with every chemical reaction as long as the temperature doesn't change. If the temperature does not change, then this constant is equal to the products in the numerator and we use square brackets to mean equilibrium concentrations in molarity. And each one of these will be raised to its respective coefficient power. And in the denominator, we put the reactants. At constant temperature. So this was very, very reliable mathematics for judging the equilibrium of any given equation. And I lost my train of thought. Okay, I probably got a slide on it anyway. No, that's not what I was hoping for. Remember the energy diagram that we drew? Okay, I'm gonna put the K on the other side. So I can draw the energy diagram. Remember we had reaction progress and energy here. And we had reactants and products. Okay, and then we went through an activation energy. And once we reach that, and this is here is the activation energy. Once we reach that activation energy, and then the reaction can go. What I want to show you in this diagram is the difference between kinetics and equilibrium. What part of this diagram are we actually concerned with? This part here is kinetics. The speed of the reaction is determined by, let's see, somebody raising their hands. Yeah, where is it? There it is. There's my chat. Oh, I guess not. Okay. Or did I raise my own hand? Maybe I did that. Okay. All right, never mind. So kinetics, the speed of the reaction is dictated by the activation energy. The equilibrium discussion hinges on before and after. So equilibrium is here. There and there. What that means is when we're concerned with equilibrium, we're not saying anything about how fast the reaction occurs. We're just saying this is where it sits once the balance is established. How fast it gets there is another discussion with kinetics. So, to illustrate the point, diamond is kinetically unstable. Right? It will eventually revert to an elemental carbon. That's what equilibrium tells us. But kinetics tells us that it'll take millions of years for it to happen. Okay. All right. If we write the reaction in reverse, say we need remember Hess's law when we were wait a minute, we haven't got we did. Hess's law for combining reactions and determining the enthalpy of a reaction by combining individual reactions. Sometimes we have to flip them and multiply by a constant. If we flip them, then the equilibrium constant is inverted. And it makes sense, right? If we put the products over on the reactant side and the reactants on the product side, then that just changes this order. So that means if we reverse the equation, then we just invert the K, just 1 over K. If, on the other hand, we have to multiply the equation by a factor, say a factor of n, say we have to do this. What does that give us? Well, that gives us NA, NB, NC, and ND, right? Okay. Now, what does that do to the equation? Well, there's an N here, there's an N here, there's an N here, and there's an N there, right? Okay. So the rules of mathematics say that we can factor out that N, which means we can pull that N out. And do that, right? So this expression in here is still K to the N power. So then we raise K to the N power. So if we have to multiply, in order to combine equations, if we have to multiply by a constant, the constant becomes the power of the new K, well, power of the old K to yield the new K. And the other thing that I need to point out is, you see how complicated this expression can get. If you have several reactants or products in here, and each one to its own power, the units of measure can be unwieldy. So by convention, the K value does not report units of measure, which means you have to be extra careful about doing your calculations. If you take great care, then the outcome of a calculation will be correct in its units of measure. And it also depends, up to this point, we've been talking molarity, right? Molar this, molar that, molar that, molar that, to a power. But if there are gases involved, we can also express them as partial pressures. Right? The partial pressure is another way of expressing the concentration of a gas in a mixture. So if that's the case, then we say something like this. We'd say the pressure of C, or C, to the C power. Partial pressure of C to the C power. And those units are usually atmospheres. They don't have to be, but usually are. And in that case, the K is going to be different because you're starting off using a different system of measure. All right. I mentioned this before, temperature. As long as the temperature is constant, the K will be constant. That's the only variable that changes the K. Now, there's a difference between, let me see, I'm going to have to erase some of this. Make room. I'll redraw that if I have to. There's a difference between the concept of equilibrium constant, K, which is a constant for any given temperature, versus equilibrium position. Equilibrium position, remember the earlier slides we had on if we add a reactant or we add a product. The equilibrium constant is going to be the same, but the equilibrium position will change. And by that, I mean the concentrations, the values that we assign or that we measure for each of the reactants and products after we've disturbed the reaction and it reestablishes equilibrium, the concentrations are not the same as they were before. That means we have a different equilibrium position. Okay. The K values, some of the K values have subscripts that tell you something about the reaction that they reference. KEQ is just a general. We want to put an EQ down there if we don't have any other subscript, just so that we don't mistake it for a different K, like the rate law K, which is usually a small K, but it can get confused. So a KEQ is just a general equilibrium constant. Water dissociation has a KW. And that we're going to look at that in more detail in chapters 14 and 15. Water, pure water, is in equilibrium with parts of the molecule that can break away, right? So we're reserving that one for water dissociation constant. Acid dissociation has a subscript of A. So if we have an acid, it can be in equilibrium with its parts. Now that's an abbreviated version. It's not actually what you see in solution, but it illustrates the point. Solubility product. We're going to cover that in chapter 16. Right? That's reserved for solubilities. And formation constants, K sub F, is reserved for formation constants. Those are where usually a metal and some ligand or another group is attached to it with a given molar ratio. Like you may have for each metal, you may have 1 or 2 or 3 or 4 associated with it, and that's a fixed ratio. So, and we form that complex species, and it is in equilibrium with the individual parts. So we reserve that one for formation constant. And then lastly, K sub P is that K that we are talking about when we use units of partial pressure instead of molarity. There are some others, but those are the major ones and the ones that we're only concerned with in this course. So here's a way you can write the Haber-Bosch equation. If you're using partial pressures, we would say, now in this case, we've got parentheses around the pressure values. I tend to leave parentheses off. I would write it Kp equals P for ammonia squared divided by P from nitrogen to the first power times P for hydrogen to the third power. The reason I don't like to put parentheses in there is because I have parentheses reserved for something else. When we have square brackets, that is equilibrium position concentration in molarity. If I use parentheses, say I use this, say like that. I use that for non-equilibrium concentration. And that's going to be useful subsequently when we talk about how to determine the equilibrium position of the various reactants and products. Right, that's coming. But I like to reserve the parentheses for non-equilibrium situation. Okay, so if we measure the partial pressures of these gases in this reaction mixture, and we find that they are these values here, then we can calculate their K sub P. Right? And that K sub P will be this value. We're going to talk about what that means in a qualitative qualitative description. Now these values, these KEQ for molarity and KP for partial pressure, can be related if we know the equation and we know the change in the number of the coefficients of the gaseous reactants. Then we can equate them, right? So the equation, let's see, I'm going to leave that one there. And Kp then is equal to Keq RT to the change in N. Let's see. That delta N is the sum of the coefficients of the gaseous products minus the sum of the coefficients of the reactants. So if you have, let's see, a higher value for, well, in this case, products is 2, right? And then we subtract 1 plus 3. Okay? Right? These are the reactants. That's equal to a minus 2. So that value would equal minus 2 for this reaction. So that delta N can be a positive or negative. It just depends on the coefficients of the gaseous reactants. Now, we typically, if you have a mixture of a solution and a gas, we usually opt for molarity. We only use Kp calculations for reactions that are 100% gaseous. Or, and I might, let's see, we have to use the 0.08206 value for R, and temperature has to be in Kelvin. Let's see, I think I missed a point in here somewhere. Yeah, I bet it's back here. No. I glossed over it somehow. Okay, concentrations, all right. All right, I'll just describe it then. When we're putting our terms into the expression, there are two situations where we do not introduce variables from the chemical reaction. If one of the reactants or products is a solid, we don't put that in the expression. if it's a pure liquid. We don't put that one in either. The reason being that these concentrations do not change. Right? If it's a solid or a pure liquid, the concentration is constant. So we don't introduce those into the reaction. So if it's a gas or if it's in solution, then we introduce those into the expression as variables. Okay, so if we use the calculated value that I mentioned earlier, 2 minus 4 would be a minus 2, so we'd have the 0.08206 times 308, which is the temperature that's given to us at 35 degrees. Then we take that to the negative 2 power, and we have K as our unknown, and we're setting it equal to the K sub P that we calculated earlier. Then we solve for K, and we find that, lo and behold, it's a completely different value, 2.5 times 10 to the 7th. All right. Okay. In a homogeneous equilibrium, all of the reactants and products are in the same phase. That is, they're either all gases or all solutions. Now, we're going to stick with aqueous solutions, but it doesn't have to be aqueous. For our purposes, we're going to stick with aqueous or gaseous. Here's a situation, and I bet the slide I was looking for is just coming up. Here's a situation where potassium chlorate decomposes into potassium chloride and oxygen gas. Right? The only term in the equilibrium expression here is the gas, because potassium chloride is a solid, potassium chlorate is a solid. They're not considered for equilibrium. Here we have water is decomposing into hydrogen gas and oxygen gas. Water's not included in the expression. This is what we would see. There it is. Solids and pure liquids are not present in the expression. So this K value is only the concentration of oxygen. And I guess we left the other one out, but the point is made. Now, we can derive some information simply from the fact that the K value is either a very large positive value, positive power of 10, or it's a very small value, negative value of 10. If it's a very, we'll use this as our example. Right? If this value is very large, which we found it was at 35 degrees, that means what? Based upon the way this equilibrium is written, a very large value means a very large numerator. That is, large K says that the forward reaction, the products, are favored. And we have very little of the reactants left at equilibrium. It goes the other way, and the reaction essentially goes to completion. If it goes the other way with very small value, okay, the other situation predominates. The reaction is not favored. It doesn't go to products. So this would be a very small value, this large value, that gives us a small K. And these values can change for the same reaction. They can change depending on the temperature. So you could go to a very high temperature, favor products, go to a very low temperature, favor reactants. So if the equilibrium lies to the right, the value of K is large, greater than 1. I say it needs to be much greater than 1, because the way that the K is constructed, just saying it's greater than 1 doesn't tell you much. But if you say it's very large, then you're pretty sure that it favors products. And if it's very small, then it favors the equilibrium lies to the left or the right. Now, it's important that when you say equilibrium lies to the right or equilibrium lies to the left, that you're referencing a balanced equation. Because if I flip that equation and you say to the right, then you're wrong. Right? Right? You're wrong. So it's important that if you say right or left, you're referencing an equation right there with the words right or left. Okay, now that we've established how to calculate a K value at equilibrium, suppose your reaction's not at equilibrium yet. Suppose you just started and you put a certain concentration of reactants and maybe a little bit of product in there. We can use the same math that we do for the equilibrium constant, only now we substitute non-equilibrium concentrations. And instead of giving us a K, we call it a Q. So Q then would be, and try a different. Q then would be C, D, A, B, parentheses, C, parentheses, D. There you go. That's where I like to use my parentheses, because that means we're not at equilibrium yet. And you can calculate do the same calculations for a non-equilibrium situation, and then you can compare that Q to the K and say something about which direction the reaction is expected to go. Because if you put in a lot of product and a very little reactant, then maybe it's going to shift to the left instead of the right. And knowing the Q value can tell you something about that direction. Right? The obvious one is if Q is equal to K, then you're already at equilibrium. That's very difficult. It's really theoretical because of experimental error, measurement error. When you put reactants together with products, you think you have a certain amount, but you don't necessarily have that. But for argument's sake, if Q is calculated to be equal to K, it's at or very, very near equilibrium. If Q is greater than K, the shift should go to the left. Why? Because Q means you've got more product than you do in the K situation relative to the reactant. This is too big, this is too small. So that means you've got more product than you need. If Q is greater than K, it moves to the left, as written, and vice versa. If Q is less than K, it's going to shift to the right. Now, understanding how to use this is important for us coming up for calculation purposes. And I'll show you what that means in 2 seconds, as long as it takes me to get a drink. So, consider this reaction. Iron 3 plus ion and the thiocyanate ion combine to make a complex ion. This one right here. Okay. They're all aqueous concentrations, so every term that's in this equation is in the equilibrium expression. So what's the value for the equilibrium constant for this reaction if we know, or if we were able to measure the iron 3 plus concentration at 6 molar and the thiocyanate at 10 molar, and at equilibrium we have 4 molar thiocyanate iron 2 plus complex ion. All right, here's how we solve this equation. I hope. Yeah, I did put it in a slide. That's good. What I like to do is write out the balanced equation and then underneath it, put what we know about each reactant and product. And this is where the concept of the ICE table comes in. ICE is an acronym for initial concentration, any changes that occur, and then the equilibrium concentrations that result. So, and I said that wrong in the previous slide. Those are not equilibrium concentrations. Those are, well, the complex ion is an equilibrium concentration. The 6 molar and the 10 molar are not equilibrium. So in the ICE table, we would put 6 molar underneath the iron, 10 molar underneath the thiocyanate, and at the beginning, there would be no product. That's 0. So what changes? Well, which way is the reaction going to move? We don't have to calculate Q for this one, because if there is no product, the reaction would move to the product side. It may be a small movement, but it's going to move that way. Okay. We are also told the concentration here of the equilibrium concentration of the ion. So that means that we put 4 here, and that means the change had to be 4 plus. We had to add 4 to this side of the equation to get 4 at equilibrium. Okay. So where did it come from? Well, the ratios are 1 to 1 to 1. So it had to come 4 from the thiocyanate and 4 from the iron. So that means we subtract that from the iron and subtract 4 from the thiocyanate to give us 4 as the product. Now we can calculate the equilibrium concentrations. Iron now is 6 minus 4 is 2, and thiocyanate is 10 minus 4 is 6. So the equilibrium position for this reaction is 2 molar iron, 6 molar thiocyanate, and 4 molar thiocyanate iron 2 plus ion, 3 plus ion, excuse me. Okay, so now we can calculate, based upon the law of mass action, what that equilibrium constant should be. We just plug in the values of the equilibrium values, and the K then is 0.333 for this reaction. So what does that tell you about the equilibrium position? It tells you that the reactants are preferred. Not by much, but reactants are preferred. All right, now that we have the equilibrium constant, we can set up a different situation. Right? We can say, all right, now we're going to do the whole experiment again, and we're going to put 10 molar iron 3 plus and 8 molar thiocyanate at the same temperature. We want to know what's the equilibrium concentration of the complex ion. So we set our table up again. The initial concentrations are 10, 8, and 0. And we don't know what the change is yet. So we're saying we know the stoichiometry. So if we lose X from iron and lose X from the thiocyanate because they are 1 to 1, then we're going to end up with adding X at the complex ion product. So we bring those down. X plus 0 is X. 8 minus X is 8 minus X is the equilibrium concentration for thiocyanate. 10 minus X is the concentration for iron 3 plus. So if we take our equilibrium expression and plug in these algebra expressions, X would be in the numerator, 10 minus X and 8 minus X in the denominator is equal to 0.333. All right. I think you can see right off the bat that we're going to end up with a quadratic equation. All right, and here it is down here. X squared, X, and a constant. If we use the quadratic solution, right, and I have it on the back of my calculator. Well, that's not my calculator. Let me see. Is it the back of this one? Yeah. I keep it on the back of my calculator because I can't be relied upon to remember. So if this is A, this is B, and this is C, then the quadratic solution is minus B plus or minus the square root of B squared minus 4 times A times C. All of that divided by 2A. And we get two answers, right? Because of this plus minus. We get two answers. Then what we have to do is decide which one makes sense, right? If X is 15.99 or about 16, what would that do to our expression? Well, if it's 16, there's nothing left here. 16, there's nothing left. 16, there's 16, and there's nothing in the, there's nothing for the denominators, right? And anything divided by 0 is infinity, so that doesn't work. So the other option is 5. 5 would work, right? 10 minus 5 is 5. 8 minus 5 is 3. And 5 is equal to X. So that's the concentration of the complex ion. I'm going to show you another method coming up. This works okay when you have a quadratic. But if you have an expression that turns out to be a cubic or higher, then there is a cubic equation for the solution, but it's a monster. And it only gets worse beyond that. So I'm going to show you another method. It's called the method of successive approximations. And it worked great. In fact, most chemists, when they're studying equilibrium of very complex reactions, they have computer programs set up that will take the values for this particular reaction and will crunch the numbers for them in just a few seconds. But we're going to do it by hand for a sample problem coming up. Okay, so if we change the values, we're going to have a different equilibrium position, which means a different concentration for the complex ion. And if we go through the same procedures as we did before, we find out instead of 5, we're going to have 3 molar, a different equilibrium position. The constant's the same. The position is different. Okay, so this is just a general layout of how you solve equilibrium equations. Same as stoichiometry. Balance your equation first. You got to have a balanced equation with all your compounds written correctly, everything in its place. And in this case, we have to designate the states: solid, liquid, gas, aqueous solution, because of the requirements of the law of mass action. We have to know which terms that we can include in the law. Then you write the equilibrium expression based upon that balanced equation. You find out what the initial concentrations are, build your ice table. If necessary, calculate Q. If you have values for every reactant and product, then you need to calculate Q so that you know which direction the reaction is going, because that will influence the calculation later, the way the ice table is constructed. If one of the reactants or products is missing, then you know which way the reaction's going. It's going toward the side with the missing. Unless you have missing on one side and one on the other side, then you will have to go to a Q calculation. But usually I'm not going to give you one unless of that nature, unless just one is missing. Okay. Then with your ice table, you define the change that's needed to reach equilibrium, right or left, and substitute the concentrations into the equilibrium expression. Once we've established which way it's moving and we've chosen our unknown, choose your X value. If at all possible, choose the X value to be the answer to the question. Okay. So if it says, what's the concentration of this product? Make that X. That's not always possible, but wherever possible, do it. Because if you can't, then you come up with an answer and use that answer to determine to answer the original question. And then check your calculated equilibrium concentrations by plugging them back into the K expression and being sure that you've got a K value. All right, here's the same equation, and it gives us practice, right? I'm not going to go through all these. It's just we got different equilibrium positions. We've got values for the product. So we're going to have to calculate Q's for each one and say which way they move. Let me see if I did one of them, maybe on the next slide. It just gives the answers. Maybe we ought to do one of them. Yeah, let's do one of them. I think we got time. Okay, so we write the balanced equation. Let's see. Iron 3 plus and iocyanate and iron iocyanate iron. Notice that we have one negative here and a 3 plus. When you put them together, you've got a 2 plus. It balances. Okay. So if our initial concentrations are 9, 5, and 1, 9 molar, 5 molar, and 1 molar, then we will calculate the Q. Okay. So the Q is going to be that 1 over 9 times 5. Okay. So 1 divided by 45. I think it's pretty certain. Yeah. That's 0.022, which is smaller than the K, which means what? If it's smaller than the K, then it's going to move to the right because we don't have enough of this. It's too small. So we need to move to the right. Okay. We've determined that. All right. So the change and the equilibrium come next. So if we're going to find out concentrations of every component, then it really doesn't matter where we put the X. We're going to have to do a calculation for each one anyway. So let's say we're going to add X there. That means 1 to 1 to 1. We're going to subtract X here, subtract X there. So that means 9 minus X, 5 minus X, and 1 plus X. Okay? So now I'm going to run out of room. So I'm going to have to erase some things once we start calculating. We have to keep these right here because once we find out what X is, then we got to calculate each one. So yeah, I'm going to have to erase some stuff. I'll put it up here on top. Okay, so the the K of 0.333 is equal to 1 plus X over 9 minus X times 5 minus X. All right. So if we expand the polynomial, we still have 1 minus X up here. But down here we have what? Well, 5 times 9 is 45. All right, so that's the constant in. X squared. And then in between we have a minus 9 and a minus 5X, which is a minus 14X. Like that. Okay? So now if we multiply 0.33 times those, we get, bring this over here, 0.333x squared minus 14 times 0.33. 4.662 x plus 0.333 times 45 is 14.985 equals 1 minus x. Okay, so let's see, I need to put this down here. 9 minus x, 5 minus x, and 1 plus x at equilibrium. All right, so if we say we're going to bring this over here, then that's a minus 1 on this side and a plus x on this side. So a minus 1 to this side would be 13.985, 0. And a plus x on this side would be a minus 3.662x. And then 0.333x squared. All right. Minus b. So that's a plus 3.662 plus or minus square root of 3.662 squared minus 4 times 0.333 times a minus 3.6, no, C, excuse me, times 13.985. Okay. All over 2 times 0.333. I'm not going to waste time solving the problem, but I do want to get it set up correctly. So let's try that one more time. We have iron, thiocyanate, yields FeSCN. 2 plus. There we go. So initially we had 9, 5, and 1. Okay. The change, we're going to add some on that side. We're going to subtract some here, subtract some here. So at equilibrium, we have 9 minus x, 5 minus x, and 1 plus x. That seems reasonable. Yeah. Now, did we calculate the Q correctly? Maybe that's where I went wrong. So what should the Q look like? The Q should have 1 divided by 9 times 5, because everything's to the first power. I think I did this one correctly also. 1 enter 45 divide. Yeah. 0.0222. Right. Small q means that it's going to move that direction. Okay. So then our k would look like this. 1 plus x, oops, divided by 9 minus x times 5 minus x. There you go. And that's equal to 0.333. So, excuse me. If this is 4, that means x was 3. Yeah. This would be 2, and this would be 6. Okay. I'm going to leave the number crunching to you guys. And we're going to carry on before I use up all our time. Since I can't see anybody, I'd have to assume that you guys are staying with me. Okay, what do we got here? A concept check. 2 moles of ammonia is introduced into a 1 liter container, which means what's the ammonia concentration? 2 molar, right? At a certain temperature, the ammonia partially dissociates according to this equation. All right, so it's the Haber-Bosch in reverse, but that's not balanced. So it has to be ammonia would be in equilibrium with, let's see, they've got nitrogen first. This is a gas, nitrogen gas plus hydrogen gas. Right. This is going to be 2, and this is going to be 3. So at some given temperature, this is the equation that occurs. And initially, you have 2 molar ammonia. And you don't have any of this. All right, so we know which direction the reaction's going. At equilibrium, you have 1 mole of ammonia remaining. Which means 1 here. Right? That's what's left. So the change that's occurred here is this lost 1. Right? Which means if we lose 1 here, how many are we going to get there? Well, it's 2 to 1, so this is only a half. Right? And this is 3 to 2, or 3 to 1 would be easier, plus 1.5. Okay, everybody follow me there? So that means at equilibrium, we have 0.5 and 1.5. And it's just a simple matter of constructing the K expression. And you should come out with 1.69. We did the K. We did the K for this one in the other direction. In a previous slide, in other words. Okay, how about this one? We've got 1 mole sample of dinitrogen tetroxide placed in a 10-liter vessel reach equilibrium according to this equation. K is given. Calculate the equilibrium concentration of the products. This one should be fairly straightforward. All right, so we have this equation, N2O4. I'm not going to write gas because we know both of them are gas. Oops. All right. And the K is 4 times 10 to the minus 4th. So we have initial change equilibrium. Initially, we have 1 mole in 10 liters, which is 1/10 of a mole. Molar. 1/10 of a molar. Let's see. 3 significant figures. 1/10 molar, nothing there. Okay. Let's see. It's allowed to come to equilibrium, and we have the K value. Okay, so we should be good. All right. If we know it's going to go that direction. So if we lose a certain amount of this one, twice as much is going to show up on this side. So this is 2x, and this is 0.1 minus x. Okay. So our expression is going to be 4 times 10 to the minus 4th equals this one squared, 2x squared, divided by 0.100 minus x to the first power. Okay? Okay. Here's where we can approximate. We know that the K is very, very small, which means very little of that is going over here. So that term right there, that x is going to be extremely small, right? 10 to the minus 4th is going to be very small. So what we can do is this one goes away. There we go. Okay, now 0.1 times this one is 4.00 times 10 to the minus 5 equals 4x squared. So x squared is then equal to 16 times 10 to the minus 5, right? No, it's equal to 1. 4 divided into 4 is equal to x squared. So square root of 1 times 10 to the minus 5 is then x equals 0. Actually, scientific notation, 3.16 times 10 to the minus 3. Okay, so 2 times 3.16 times 10 to the minus 3 is 6.32 times 10 to the minus 3, correct. And then this side is going to be 0.1 minus x. Let's see. I'm going to do x again. Exponent 3.16, 10 to the minus 3. Subtracted from 0.1 is 0.097. Okay, that's correct. All right, what I was trying to show you was how to avoid quadratics. And my mistake was estimating the wrong one. I should have left this one alone and said that one right there is going to be so small that it's insignificant. Okay. Then we can estimate by just saying 0.1 instead of 0.1 minus x. That gets rid of the quadratic problem. Then we just have a square root. Okay, now how do I know that this estimation is accurate, is within acceptable limits? Well, there's something called the 5% rule. And I thought I had a slide on it. What we're saying is we're estimating let's see, our two values. Let me just put our two values up here. So our two values now are 0.097 0.097 molar, and NO2 is 6.32. 6.32 times 10 to the minus 3. Okay? That's what we think it is. What we need to do then is to put these numbers into the law of mass action for this equation and compare them to the actual K. So if we calculate the K using those values, we're going to have, let's see, this is squared, isn't it? Yes. 6.32 times 10 to the minus 3 squared over 0.097 molar. So let's see what that is. 6.32 exponent minus 3, and I square that one. Okay. And then I divide by 0.097. And that gives me 4.12 times 10 to the minus 4. Okay. The actual K is 4 times 10 to the minus 4. We've got a little bit higher number. The question is this number less than or greater than 5% of the 4? So we look at what's the difference between 4.12 and 4 is 0.12. So we just say 0.12 divided by 4 times 100. Because they're both the same power, we can do that. 0.12 divided by 4 times 100. That's 3%. So our estimate is valid. We just try to get within 5%. Now, if we want to get closer, then we can use the successive approximations method. We can take this value that we determined here for these two values and put them into the ICE table, calculate a new equilibrium concentration, and then compare them, and I guarantee that they will come out smack on that value. I've done it before. But the biggest problem for me right now is board space. I can't spread out like I used to. What we'll do is next Monday, we'll take the review document, which is in Brightspace, and we'll work some of these problems out in detail on the board, weather permitting. I need to get another marker. These markers are failing. Okay. Now, that earlier question where I said, what would happen if you add this reactant? Or what would happen at equilibrium? what would happen if you add this reactant or that product, and we came to the conclusion that it would move one direction or the other. That is an expression of Le Chatelier's principle. Le Chatelier says your starting condition is equilibrium. If you do anything to disturb that equilibrium, the system will respond. And it will respond in such a way that the equilibrium will shift to reestablish whatever direction is necessary to reestablish equilibrium. So if we add a product, we're disturbing it in such a way that it moves to the right. And it will keep moving to the right until equilibrium is reestablished. Or if we add product, it'll do the same thing, only in the reverse direction. That's Le Chatelier's principle. And there are three conditions that we're going to investigate here to determine which way a reaction will move when we disturb it. One is concentration. We've talked about adding something to one side or adding to the reactant side or the product side. But what if you take away something? Say we remove. Say we've got the Haber-Bosch process here. We've got nitrogen plus hydrogen yields ammonia. 2. Yeah, that's right. Okay. We know what would happen if we add this or add this or add that, which direction it would go. But what if we remove? What if we remove ammonia? That's what Fritz Haber did. We remove ammonia, then we're decreasing this concentration, and the imbalance now forces the shift to the right to replace it. Okay? When Haber was developing this process, he increased the temperature to, I think, 800 degrees C. And he used a catalyst. Finely divided iron as his catalyst. And he was able to produce a certain amount of ammonia. Well, the way he kept the shift going toward ammonia, because that's the product he wanted, was he bled off the reaction mixture, right? Bled off some of this whole, as it produced ammonia, bleed it off and cool it. And he cooled it in such a way that only the ammonia condensed. Right? It takes a lot lower temperature to condense nitrogen and hydrogen, so he just cooled it enough to remove the ammonia. And then he fed the products, which are now reactants, back into the system. And it kept cycling toward ammonia. Excuse me for just a minute. Come here. Come on. Let go. It's like having a 2-year-old running around under your feet. Okay, so that has to do with concentration. We've talked about adding or removing. Now, another condition that can affect the equilibrium. Oh, I got a video. All right, I forgot I left this in here. No? No?
Le Chatelier's principle states that if you have a reaction equilibrium and you apply a stress to that equilibrium, the reaction will shift in a direction in order to relieve the stress. We will look at a series of different reaction equilibria. We'll apply a stress to those equilibria and see in which direction they shift. In the reaction between iron plus 3 ion and thiocyanate ion, if we add some iron plus 3 in the form of iron 3 nitrate and to the iron 3 nitrate add some potassium thiocyanate, the two react to form a reddish-orange complex ion. We filled two test tubes with the reaction mixture. We're going to keep one test tube as a control so that we can see what happens to the color. To the other tube, we're going to add some 0.1 molar iron nitrate to increase the concentration of the iron. We see that there's an increase in the dark red color. This indicates an increase in the concentration of the complex ion. This also indicates that the reaction has shifted in the forward direction. As you add reactant to an equilibrium, the reaction shifts in the direction to use up the added reactant, in this case the forward direction. Now we'll add 0.1 molar potassium thiocyanate to the second tube. This increases the concentration of the thiocyanate ion. We see that the reaction mixture turns a darker red color, indicating an increase in the formation of the complex ion. We've added the other reactant, the thiocyanate. The reaction shifts in the forward direction to use up the added reactant. We will now add some 1 molar sodium hydroxide solution. We notice that the red color decreases significantly. This indicates that the reaction equilibrium has shifted in the reverse direction. The hydroxide ion precipitates the iron ion, effectively removing it from the solution. The equilibrium shifts in the reverse direction to try and increase the concentration of the iron. We will now add solid potassium chloride to the solution. We notice the decrease in color indicating that the reaction has shifted in the reverse direction. The chloride ion forms a complex ion with the iron, effectively tying up the iron concentration. The equilibrium shifts in the reverse direction to try and replace the iron that's been removed. We will now add 0.1 molar silver nitrate to the reaction mixture. We notice the disappearance of the red color, which indicates that the equilibrium has shifted in the reverse direction. We also see the formation of a small amount of white solid. The silver ion reacts with the thiocyanate ion to form slightly soluble silver thiocyanate, which is the white solid. The silver ion removes thiocyanate from solution. The equilibrium shifts in the reverse direction to try and replace the thiocyanate ion that's been removed. We will now add some 0.1 molar mercury 2 nitrate. The mercury plus 2 ion reacts with the thiocyanate ion to form a new complex ion. This effectively reduces the concentration of thiocyanate in the solution. The equilibrium shifts in the reverse direction to try and replace the removed thiocyanate.
Okay. We're going to do a lab of the Le Chatelier's principle lab, which is going to be an informal lab, so it doesn't require a formal report, and investigate some of these and some other types of reactions, essentially qualitatively. And one of the principles that operates here that allows us to reduce concentrations of some of the components, reactants or products, is what's called a coupled reaction. We use a reaction that efficiently removes a reactant or a product from solution so that we can see what happens as that concentration is reduced. All right. Another factor that comes into play is temperature. Now, temperature, once we reach equilibrium, temperature will affect the equilibrium situation. My video looks like it's freezing. And that's troubling. Is it still recording? Shoot. Okay, I think we're back. All right. So, in case this part got cut out, I'll go back to the beginning of this slide. Temperature affects the equilibrium by affecting the equilibrium constant. Now, there are two ways to approach this. One is to say what happens to the equilibrium constant when we change the temperature. The other is to use a rule of thumb and count temperature change as a component, either a reactant or a product. That's the one I like to use. But I'm going to talk about both of them so that you understand why the one used, why the rule of thumb works. So if we have a reaction, let's say, let's go back to the Haber-Bosch reaction. Hydrogen yields ammonia. And this is 2 and 3. Okay. The equilibrium is established. Now, this is an exothermic reaction, right? Exothermic, which means it gives up heat. So I make heat a product for an exothermic reaction. Now, if I change the temperature, I can assess the effect of the temperature on this reaction. If I increase the temperature, it's going to drive the equilibrium back this way. Okay? That was Haber's problem. He knew he had to increase the temperature for the kinetics of the experiment, because without a certain temperature, then we wouldn't reach the activation energy, or you wouldn't have enough atoms or molecules exceeding the activation energy to yield a product. But he knew that the equilibrium would be shifted back this way because the reaction was exothermic. So that's why he introduced the catalyst. The catalyst then lowered the activation energy, so the temperature would generate more activity in that direction, even though the equilibrium was low. And then the final step was to remove ammonia continuously from the reaction mixture so that we drive the equilibrium that direction. Okay, so when we change the temperature, if we know whether it's exothermic or endothermic, then we can assess the effect of temperature. Decreasing the temperature on this reaction will shift the reaction to the right, toward the product. If we flip the reaction and make it a decomposition of ammonia, then it becomes an endothermic reaction. And increasing the temperature will drive the reaction toward nitrogen and hydrogen. Now, why does it do that? Well, let's look at the equilibrium constant. Okay. What happens to this reaction if we change the temperature? If we change the temperature, if we increase the temperature, then we're changing the K. The K is at a certain temperature. Let's say T1 is less than T2. Right? The original temperature is T1. The change that we're going to make is to T2. and T2 is higher than T1. If T2 is higher than T1, then we're going to reduce the amount of product. We're going to make that less. So K1 then will be greater than K2 because we're making this one smaller. All right. An exothermic reaction will do that. If we add energy here in the form of temperature, we're making less of this, which makes this smaller. And by increasing the temperature, we're actually decreasing the K value. And that equilibrium, we know, with a smaller K, shifts toward products. That's what's actually happening in the reaction when we change the temperature. But that understanding is not going to answer a question quickly on an exam, whereas the rule of thumb will answer the question very quickly for you. The last condition that we're going to change to disturb an equilibrium is pressure. This is a gas, this is a gas, and this is a gas. Okay? Let's just remove those and leave that up there. Okay. If we're at equilibrium in this situation, what matters is the total number of moles of product versus the total number of moles of reactant. So in this case, we have 2 moles of gas on this side. In this case, we have 3 plus 1, or 4 moles of gas. Okay? And we're keeping the temperature constant under these, in this scenario. So if we increase the pressure by decreasing the volume, right, the system is going to want to alleviate some of that pressure. And the way you do it is by Avogadro's law. In other words, you reduce the number of moles of gas. If you can reduce the number of moles of gas, that will reduce the pressure and relieve some of that stress that we've applied to the system. So by increasing the pressure, decreasing the volume, that's Boyle's law, then which way is it going to shift? Increasing the pressure says that it's going to try to make more product to alleviate that pressure. So in Bosch's scenario, one thing that I left out was the pressure. He increased the pressure to several hundred atmospheres, which he knew would favor the product side. Because 2 moles is less than 4 moles, we increase the pressure, it goes to fewer moles to relieve some of that pressure. Okay. If, on the other hand, what happens if we decrease the pressure by increasing the volume? If we do that, then it wants to make more moles. So it would shift over to this side to make more moles. That's how pressure affects the change in pressure affects the equilibrium. Now, one thing I didn't say was make a point of 3B. If you add an inert gas to increase the pressure, does that affect the equilibrium? No. The reason it doesn't affect the equilibrium is because you've increased the pressure, but you haven't increased the concentration as a consequence of changing that pressure. The inert gas is not a reactant. It's not a product. It has nothing to do with the reaction. So you haven't affected the equilibrium at all. And that also goes for reactions where you have a mixture of, say, solids and gases or liquids and gases. You only have to consider You only have to consider the gas component when you're talking about changes in pressure. Okay, that was my last slide.